All right, everybody, thanks for coming out tonight to learn about astronomy. And I'm very happy to tell you about gravitational lensing, which in my view is one of the most fundamental and also one of the most visually striking phenomena that we now in modern day cosmology astronomy research, we routinely observe this. And so I think it's great you're here tonight to learn about this, even if you never heard about it before. So I give this the title, Seeing the Invisible Through Gravitational Lensing, and a subtitle, Cosmic Magnifying Glasses and Einstein's Optical Illusions. I hope by the end of this presentation, all of these words will make sense to you. If not, definitely do feel free to ask questions towards the end. All right, so gravitational lensing effect can actually be summarized in just one simple sentence, which is light bends around massive objects. And this is one of the direct predictions by Einstein's general relativity theory, which he published around the years near 1915. And here is a picture of Einstein doing very serious math on the chalkboard. And this photo actually was taken at Carnegie Observatories, as Cameron was introducing earlier, which is 2 miles north of here. And if you've never been there, Carnegie Observatories every year in the fall around October, they have an open house event. You can go in, you can look at the machine shops where they build a lot of instruments for the telescopes. You can look at the library, which is very beautiful, where Einstein took this photo. And in addition to Einstein, a lot of very important figures in the history of astronomy have passed through Carnegie Observatory. So I encourage you all to go there in the fall when they have the open house if you've never been. And so on the right-hand side here, if you pay attention to this figure, this is an illustrative picture showing how gravitational lensing works. So now we are on the Earth, that's towards the bottom right of this figure. And imagine if you want to observe a very far away galaxy in the background, and there happens to be a massive object between you, the observer on the Earth, and the distant galaxy you want to observe. And this massive object will distort the space-time around it. And as a result, the light rays originating from the background galaxy will not travel along a straight line anymore. Instead, it will travel along this distorted, curved space-time to reach us on the Earth. And as a result, we no longer observe the original intrinsic shape and morphology or brightness of this distant galaxy. Instead, we will observe something distorted. And so maybe this is the first time you heard about gravitational lensing, but I guarantee you have seen something very similar in your everyday life. For example, if you have ever looked through a piece of glass towards some bright object in the background, you probably have seen light distorted by the glass. And that is very similar to some of the gravitational lensing effects we observe in our astronomy observations. And in the summer, or I guess in Southern California, you can do this all year round. You can go to a swimming pool. I just moved here from Chicago and trying to get used to the temperature. So if you go to a swimming pool and you look towards the bottom of the swimming pool through the water, you can also notice the distortion effect of the water. And a regular grid of pattern at the bottom wouldn't look regular anymore. Instead, it has this distorted shape. So in a way, these very familiar everyday experiences are very similar to how gravitational lensing works. It's just in the case for gravitational lensing, you have gravity that acts as the lens instead of water or glass or what have you in everyday life. And so a key difference between these two, the general optical lensing effect in everyday life and gravitational lensing effect is that gravitational lensing is not dependent on the wavelength of the light. In other words, regardless of the color of the light, it gets bent the same way by gravity. As opposed to if you lens light with a piece of glass, that deflection angle might be dependent on the wavelength of the light or the color of the light. So that's a key difference. All right, and so I mentioned that Einstein predicted gravitational lensing in around 1915, and very soon after that, just a few years, the bending effect of light by gravity was actually already observed for the first time in human history, and it was made by a British astronomer, Arthur Eddington, also a very important figure in history of astronomy. And what he did was to observe the stars near the sun during a solar eclipse. And so it's a little hard to see, but in this photographic data he took back in 1919, he marked the location of a few stars in this photo. And what he noticed was that the location of these stars, when they get really close to the sun, they don't appear to be at their original locations when they do not appear to be near the sun. And so this is the effect that the location of their appearance on the sky were deflected because the massive star, the sun, happens to be in between us and these stars. And so this is the first time that was observed, but I didn't spend too much time digging into this, but I doubt that he was thinking about gravitational lensing effect, because roughly 20 years ago, Einstein himself published an article in Science where he worked out how much this deflection could be by a star, and he concluded that we would never be able to observe this directly. And he quoted two reasons when I actually read this article. It's short. You can also Google and read this. And it's like written in relatively simple language. So if you're curious, you can actually read this. So the two reasons he quoted for us never being able to observe gravitational lensing effect, one is that it requires almost the perfect alignment between an observer, the intervening lens, and the background source. And he said the chance of that happening is simply too low. And the second reason he quoted for never being able to observe this is this deflection angle is going to be too small, and we're just never going to be able to tell the difference with our data. And so if you ask me, maybe Cameron would disagree, I think Einstein was being a classic theorist, and he didn't have much faith, in observers and instrumentalists in their ability to really figure things out. So it turns out in the century to follow, we made much more powerful telescopes and very powerful instruments. We now routinely observe millions and coming up to billions of galaxies, and this alignment, almost perfect alignment, it's very low probability, but it does happen often enough. So we observed many of the lenses that I'm going to show you. And this very small angle in deflection with very powerful telescopes, we're also able to discern in our data. And so the observation of gravitational lensing really exploded with the invention of CCDs, which is the charged coupled device that happened in late 1970s and early 1980s. And CCDs are now the very common detector we use in research class telescopes that replaced the traditional photographic plates people used to use when they record data from the sky. And CCDs are much more sensitive and much more linear in terms of directly translating the intensity of the light to the data. And so here is the gravitationally lensed source that was observed and recorded in the late 1980s. And it's one of the most famous lenses. And here I'm showing you the same field, but this is the data taken by the Hubble Space Telescope, just to show you how much we've improved in terms of getting really high quality data. And just to point out, when I talk about gravitational lensing effect, I'm talking about how this galaxy looks really elongated. And it doesn't mean that this galaxy actually looks like this with a long tail. It's actually due to the gravitational lensing effect. It looks like this. And this effect in particular is the strong gravitational lensing effect. And this one of the most extreme versions of gravitational lensing, where you have so much mass in between the observer and the source, it distorts the light in an extreme way, where you can get this really elongated shapes. All right. And sometimes when you have also near perfect alignment between observer, the lens, and the source, you can also get a ring-like shape, very similar to what you will see, say, through the bottom of a wine glass. And this shape, we call it Einstein ring in gravitational lensing. And sometimes if they don't form a ring, you can also maybe observe multiple images of the same thing in the background. And now I'm going to show you a couple of these examples. So the prime example of Einstein ring is the source called cosmic horseshoe. And now this is real data. So in this picture, the orange-looking elliptical galaxy in the center, that is the foreground lens. So this galaxy sits between us and the background source. And the background source is this blue ring-look-like galaxy, and it doesn't mean it looks like this intrinsically. It's probably just a relatively regular-looking galaxy in the background, but it gets lensed and distorted by the orange galaxy in the foreground, and instead we observe this ring shape. And we have this very cute lens, one of my favorite. It's, people call it cosmic smile or Cheshire cat. In this case, the two galaxies, and I think in addition to some smaller galaxies in the center, they act as the lens, again, in between us and the background galaxies, and those really elongated extended arcs, they are lensed by the background, they are lensed from the background and by the foreground galaxies. And sometimes we have even more extreme lensing effects by a cluster of galaxies. These are really, really massive objects in the universe, and they can induce very strong gravitational lensing effect. And so, for example, this really elongated arc is actually from a relatively low mass galaxy in really far away universe. And because it passes through a foreground cluster of galaxies, and the cluster of galaxies has so much mass, it stretched this galaxy into such an extreme shape, and we're able to study it in very detailed way. And sometimes, as I mentioned, you can also just get multiple images of the same thing that can look a little bit different. For example, in this cluster field, which is, again, a strong lensing field, and all these orange-looking galaxies, they belong to the foreground. But because of the gravitational field of this foreground galaxy cluster, you get multiple images for galaxies in the background. So for example, this one, they're all taken from different locations in the field, but they are actually the same thing in the background. They're just multiple images of the same galaxy. And strong gravitational lensing is so amazing and so visually striking. In fact, James Webb Space Telescope's first image, if you remember this, back in 2022, President Biden announced this image, and it is the image of a strong lensing field. So this is the galaxy cluster that James Webb took for its first mission. And you can see in this field, there are numerous, because of how deep this image is, there are numerous features of strong lensing. And so just to point out a couple, there is that really elongated, I don't know how to say this shape, it's just elongated background galaxy, and it looks like that because of the strong lensing effect. And you know, like these very elongated arcs, and this arc I pointed out because it's one of the longest and one of the most magnified in the field, and you can see in the insert. The galaxies really, I don't think we ever observed galaxies with such an extreme axis ratio in terms of the length to the width, and all of them they look like this because of the strong lensing effect. Okay. And so I showed you a lot of pictures, but you know, in astronomy, we don't just look at beautiful pictures. We actually study it for a reason. So strong lensing is super useful, in addition to being beautiful to look at. So I want to tell you two specific applications we use strong lensing for in modern day astronomy. The first application, very important, is gravitational lensing actually allows us to see dark matter. So dark matter is this materials thing that makes up for a quarter of the total energy budget of the universe. But so far we haven't directly detected it. People don't really know what's the particle nature of dark matter. And dark matter doesn't emit light, so we cannot really see dark matter with traditional observation methods. But luckily, dark matter does interact with gravity, and dark matter is, in fact, very massive. So with lensing effect, and specifically strong lensing effect, we can use the distortion of the images to try to trace how the dark matter distribution should be in order to produce this lensing effect. And so what it looks like in real life is that you would go to a strong lensing field, and you would painstakingly mark down all the multiple image locations of this field that you can observe for the background galaxies. And then you try to back out how the matter distribution should be in this field in order to produce all these images at these specific locations. Because if you shift the distribution, say you shift the shape of your glass, that distorted image will look different. So this is how we can back out the distribution of dark matter with lensing. And very often we get something that kind of looks like the galaxy light distribution, because in the real universe, actually visible matter to first order traces the dark matter distribution. All right, so that's the first application I want to mention. And the second application I want to mention is also very important. So instead of looking at the lens itself to try to study the dark matter distribution, a lot of times we can also use lensing to study the source. And this is really because, and everybody has this experience, you know, if you put something further away, they tend to get tinier, and they also tend to get fainter. And in astronomy, we try really hard to look further, and we try really hard to look at smaller and smaller things to try to understand the composition of the universe and how things come to be as the universe evolves. And so it becomes a problem at some point if you look really far and you want to look at really tiny things, you cannot see them anymore, or you cannot resolve the details anymore. And so this is where gravitational lensing can really help. And to illustrate this, I'm putting the moon. Yeah, it gets squashed, but the moon is really round, in case you don't know. This is the size of the moon for reference. And this is a very beautiful spiral galaxy in our local universe. It's called Pinwheel Galaxy. And at its actual distance from the Earth, this is what it looks like in terms of the angular size on the sky compared to the moon. So it looks roughly the same angular size on the sky. But if I put this galaxy at typical distances for the galaxy clusters I just showed you, it will look like this. And actually, I'm being generous here because it will actually look almost 200 times smaller than the size of the moon. And if I shrink that image by 200 times, you wouldn't see on this image anymore. And so this is a problem. You know, if we want to study a galaxy at that distance, but we cannot really resolve it in our data, or we cannot detect it anymore because the light just gets so faint, then what do we do? So gravitational lensing here in this context can really help, because especially strong lensing, it tends to magnify things, make them look bigger on the sky than they actually are. They also tend to brighten things, so they will give us more photons than we otherwise will receive. And for example, going back to this cluster lens that I showed you before, this is called sunburst arc, by the way, if I didn't mention it. All these different locations along this arc, some of them are magnified by more than 100 times, meaning that they appear to be 100 times bigger, 100 times brighter than we would otherwise observe without this foreground lens. So this is really amazing when we want to look at very far away things, very faint things. We're able to access a lot of information that we wouldn't be able to access. And in fact, to this day, a lot of the early universe studies, the most detailed research results come from strong lensing field, or come from, you know, serendipitous alignment of background galaxy and foreground source that we're able to use gravitational lensing to resolve a lot of details. And again, you know, if this is the first time you heard about gravitational lensing in your life, you probably have seen it before, even in pop culture. So in the movie Interstellar, you probably have seen this rendering of a black hole, and it looks like that because of strong gravitational lensing effect. So it has this very bright ring around it because gravitational lensing effect kind of warps the light emitted from this accretion disk and makes it wrap around the black hole, and you see this ring-like feature. And it's not just science fiction. We do see it in real data. For example, this is a 6.5 billion solar mass black hole image taken by the Event Horizon Telescope. And this black hole resides in the center of M87. This is a nearby galaxy. And this is the image we see through real telescopes. And that's the bright donut we see as, well, partially due to a strong gravitational lensing effect. Okay, so that's all I want to say about strong lensing. And before we close, I just want to briefly mention two other lensing effects that are equally important in modern day astronomy. And just in case you encounter it, you can be, you know, real expert after this talk. You'll be a real expert in gravitational lensing now. I'll cover all the bases for you. So the other two lensing effects I want to mention beyond strong lensing, one of them is weak lensing, you know, in contrast to strong lensing. It's not as extreme as strong lensing, because in weak lensing, we don't really see multiple images. We don't see, you know, dramatic arcs. But weak lensing distorts the shape of galaxies by just a little bit. So for example, in this left-hand side image, if we imagine all the galaxies, they're just perfectly round, then through weak lensing effect, you will see something that's a little bit squished to be an elliptical. And imagine if we can map this effect, we just go to the sky and measure the shapes of the galaxies on a large portion of the sky, also at various distance from the Earth, then we can trace out this structure called the large-scale structure of the universe. And this is actually one of the key science goals for missions like SPHERE-X, which is going to launch later this week, and Euclid, Roman, or some ground-based experiments like dark energy survey. So it's a very big, important topic in current astronomy research. And we also have microlensing in addition to strong and weak lensing. So microlensing refers to the phenomenon where the lensing is induced by a point source in astronomical settings. That means very often a star. And so if you have a star passing in front of another star, what we observe is the change in brightness of this background star due to the lensing effect of the foreground star. And now imagine if you have a planet orbiting this other intervening lens star, then the planet will induce a little deviation in the light curve of this background star. And that's actually a very effective way to detect exoplanets, so planets orbiting other stars beyond the sun. And I don't work in this field, so I might be wrong, but I think so far we have at least several hundreds of exoplanets discovered through microlensing effect. So that's all I have for you. We talked about strong lensing, we talked about weak lensing, and we talked about microlensing. And I hope now you understand why we can see the invisible through lensing effect, and why I call this the cosmic magnifying glasses. And yeah, so I'm happy to take questions.